Hey everybody, welcome to the video for section 9-2, module 9.2, and we're going to be talking about what criteria are we allowed to use to prove that a quadrilateral is a parallelogram or not, and we're going to talk about 3 sets of criteria that we can use. I want you to keep in mind these criteria because when we start to use coordinate geometry to start proving these things, it's going to be really important. Just wanted to remind you every single time, remember, in your textbook or if you're looking at the video, remember we have this resource locker here up in the corner, which will be a QR code if you have a QR scanner on your phone that you can jump right to the page for this section of your textbook resources, and that can link you to your Dr. Berger videos if you want to go back and listen to him at all, and also just a lot of other resources. Just remember that that exists for you, okay? We're going to go through the Explore here, and there are 3 proofs in this video, just like the last one. I'm going to try to go through them a little faster than the 20 minutes that was there, so thanks for bearing with me with this. The first criteria that we're going to look at is to prove that something is a parallelogram by proving that the opposite sides are congruent. So that's the first proof that we have here. Okay, so in this diagram, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I'm going to try to keep this diagram up front for us. We'll zoom in a little bit here, make it bigger. Here we go. Okay. So we start by knowing that the sides are congruent this time, and our goal is to land that it's a parallelogram. So we don't just start knowing that it is, okay? So we're going to go ahead and draw a new segment DB, so I'll do that right now. And remember, that's because we can do that because through any 2 points there's exactly one line. Now DB is of course congruent to itself by the reflexive property. Then we're going to go down and we're going to talk about why it is that AB is congruent to CD and AD is congruent to CB, and that is because those were given pieces of information. And oops, I forgot to mark that our reflexive property is in existence here, so we've got that side is congruent to itself, remember, because it's used twice. So I hope you can see that these 2 triangles ABD and triangle CDB, the top and the bottom triangle there, are going to be congruent, and I hope you can see the side, side, side proof coming through there. The next step in our proof is going to be, once we know that the sides are parallel, once we know that the sides are congruent and that the triangles are parallel, then that means corresponding angles are parallel. So we're going to go with angle ABD and angle CDB. And the reason that these angles are congruent is because of corresponding parts, theorem here. Corresponding parts of congruent figures are congruent, or of triangles are congruent, as we said, is acceptable. So as soon as we know that those angles are congruent, we're going to continue with our proof here. And let's just say we have that first pair, the second pair, ADB and CBD. If we're looking at those angles as being congruent, then hopefully you realize we can also mark the sides as parallel. And the way that we do that, because they are alternate interior angles, we're going to use one of the alternate interior angles theorems, but it's not the normal, sorry, that's an M there. It's not the normal alternate interior angles theorem, it is the converse of the alternate interior angles theorem. The reason that it's the converse, remember, is because with a converse we have our logic going the other direction. So we don't start by knowing sides are parallel, we start by knowing angles are congruent, and then our conclusion is about parallel. And I hope you can see going the other direction as well. If we're looking at this first pair of angles, ABD and CDB, so that's this one and this one, then we can mark those as congruent angles, which is going to force those sides to be parallel, okay? So keep that in mind. So now that we know that the sides are parallel, we can conclude our proof here and know that by the definition of a parallelogram, which is, remember, two pairs of opposite parallel sides, then we know that we have a parallelogram. So we've established our proof. If we go to the next page under Explain 1 here, we're going to be using the opposite angles criterion to figure out that a parallelogram is in fact a parallelogram. So again, we only know, to begin with, we only know about the angles, okay? So let's move this around a little bit. Hang on. Now this time we have a paragraph proof that we're going to be filling in here as we go. So we're going to start with, given that angle A is congruent to angle C and angle B is congruent to angle D, and you can see that they've marked those on the diagram as givens, we are going to prove that it's a parallelogram by only knowing this information about angles. So let's fill in the paragraph proof as we go here. First off, we know that the measure of angle A plus B plus C plus D has to equal 360, and the reason for that is because we know we have a polygon angle sum theorem. And just a reminder, that's our n minus 2 times 180 theorem, remember? That the number of sides minus 2 times 180, so in this case 4 minus 2, because it's a quadrilateral, times 180 is in fact going to give us 360. So we can say that that's true. From the given information that we have, we know that the measure of angle A is the same as the measure of angle C, and that the measure of angle B is the same as the measure of angle D. Then we're going to go ahead and use substitution for those two values. So in other words, the middle B and C here pretty much disappear, because if B is the same as D, then this one gets replaced with the measure of angle D, and if C is the same as A, then this C gets replaced with angle A. So we're here with the measure of angle A plus D plus another A plus D equals 360, or we can group the two measures of angle A together and the two measures of angle D together, and we know that that's equal to 360. Then it says dividing both sides by 2 gives us what statement? Let's fill in the blanks. It's that the measure of angle A plus the measure of angle D is going to equal 180. And therefore, A and D have to be supplementary. So if they're supplementary, that's these two angles that we're referring to, then we know that these two sides, AB and CD, are parallel. And remember, that's another converse theorem here. So that's by knowing something about the angles first, supplementary angles that are same side interior, and you could go ahead and extend those sides there if it helps, and consider AD as my transversal, and then angle A and angle D are same side interior angles, so this is the converse of the same side interior angle theorem, just to abbreviate a little bit. And then, of course, a similar argument is going to show that the opposite sides, AD and BC, are going to be parallel. We're just going to basically work it out differently so that instead of A plus D, we're doing C plus D or A plus B or something like that with our substitution. And that is going to go ahead and prove both of the sets the same way. So if both sets of opposite sides are parallel, then by the definition of a parallelogram, we've proven that it's a parallelogram. Let's go to the next proof on the next page. Explain 2. This is the last thing that we're going to be able to prove, and this is proving that if the diagonals bisect each other, then it's a parallelogram. So this time we know to begin with that the pieces of these diagonals are equal, that they cut each other equally. So that's our first given, that AE is congruent to CE, and that DE is congruent to BE, and we can go ahead and, of course, write that that's a given. Then, tracing out our angles AEB and CED, AEB and CED, I hope you can see that that is a pair of vertical angles, and then you've got another pair going left and right there. So the final reason for that, of course, is our vertical angle theorem. So you want to make sure you mark those angles. I'm going to zoom in so we can do that a lot easier here. So we're going to mark these vertical angles congruent. And then if I zoom back out, get back to our proof. So of course we're going to write, now that we can see the markings on the diagram, hopefully you can see a side angle side treatment happening with all four of those triangles. So in this number 3 here, we actually have a double congruence statement that we need to squeeze in, so feel free to go over in the margin if you need to. Again, I'm going to zoom in so we can write it a little neater for us. So for number 3, if we have that triangle AEB, that's the top triangle, is congruent to triangle CED, the bottom triangle, then we also have that triangle AED and triangle BEC, or CEB actually, in corresponding order, are going to be congruent. Those two congruent statements, hopefully you can see, are going to be true. Looking at the diagram again, side angle side is going to be our reason. So for number 3, we want to put a side angle side theorem. And then after we know the triangles are congruent, we can say that segment AB is congruent to CD, and segment AD is congruent to CB, and that is by our corresponding parts theorem. And that finally, once we know that those opposite sides, once we know that those opposite sides are congruent, we're allowed to say that it is a parallelogram, because that is the simple definition of parallelogram. One of the definitions is that the opposite sides are congruent. That takes us to the end of our proofs, you guys. So in the next video, you're going to encounter these ideas of proving that something is a parallelogram or not within some problems with some variables put in, okay? Thanks.